At predicting chemical reactions, we need to organize our thoughts. So the first thing we have to remember are we have the metal activity series and we have the electronegativity values. Replacement associated with nonmetals. So you have to look at the nonmetal periodic table, which would be the electronegativity values. Now, if we're dealing with metals, which would be the opposite of this, then we look at the activity series of the metal. So here you can see fluorine is already bonded with the lithium. Fluorine has a 4 value, it's a Pauling scale, for its desire for an electron. So chlorine is not going to be able to pull fluorine off of lithium. So no reaction is going to take place here. So in your notes, just write no reaction. The next one, you've got chlorine and iodine. So chlorine is right here, iodine's beneath it. Chlorine has a 3, iodine has a 2.7. So it's too strong. There's going to be no reaction here. Now the last one, you have bromine is bonded with a 2.8. Fluorine has a 4. Fluorine is stronger. This reaction is going to occur. So it's going to be K. You have to look at the charge on the potassium. The charge on potassium is 1 positive because it's found right here in this main group. And then fluorine is 1 negative. And then we know that bromine is going to be diatomic. So then we just balance the charges. So it ends up being KBr plus F2 yields KF plus Br2. Is this balanced? No, now you got to balance it. That's the next step. You see you have 2 bromines here, you have 1 here. So you have to put another bromine here. And you're going to have to put another potassium here. And now you're balanced. So that's how this works. The big part with reaction prediction, which we haven't talked about, which we're introducing today, is that you have to be able to balance the compounds. That's what makes this a little bit tricky. It takes us kind of back to the beginning of the year. So understanding this kind of leads us into real-world applications like GMOs, genetically modified, I guess you would say foods. So I'm not sure what the O stands for, genetically modified organisms, probably organisms. So what is the, I guess you would say, disadvantage of not pursuing GMOs better? Anybody know?
Less food.
Less food? Why?
Because some foods are dying off, like bananas.
Okay.
And it's harder to grow them in certain areas.
Okay. Yeah, there's
certain types of bananas.
there's things called plagues.
The ones that we
You heard of plagues?
No, they're bringing back the original banana that we actually used to eat.
I know they're cloning them. That's what.
Yeah.
Yeah. But there's also like grasshoppers that go into plagues. They're basically insects that will eat things. Honeybees will attack fruits and just bore into them, and then nobody's going to, you go to the store and you see where you got a big hole in an apple. Are you going to buy that apple? Honestly, you're not going to buy that apple.
Why not just put all of our food and stuff in the greenhouse and grow it that way?
That's expensive.
Well, yeah.
You can do that with like lettuce. Most lettuce is done that way because people don't like little things growing on their lettuce. But when you start talking about larger things like fruit trees, it's just too expensive to do that. You start talking about doing that with corn and grain. The big things that are GMO are corn and grain because those are, you just can't put those in greenhouses efficiently. So if you go away from GMO and then you have like this pest that comes into play, like a grasshopper, you're going to have to use what to get rid of the grasshopper? Pesticides. And pesticides are bad for what?
Kill the animals around them, causing the book to be made silence ring.
Yeah, and also, heck, where does it go? Where do the pesticides go?
The soil.
Into the soil, and where else?
And
Into the water. Yeah, the water is the big issue. A lot of your farms in the plains, the wells are contaminated. That is, so much pesticide has made it down into the well. They gotta like have water brought to them in a cistern. They have water trucks come to their facility because the water has to be treated. You just can't dig a hole in the ground like you used to and be able to drink the water. Double replacement are the most complicated ones to work with. If it is double replacement, then the cation and the anion switch places. It is helpful to separate each compound into their cation anion parts with their charges. That's what I always do. Like you see up here, we did this with the single replacement, separate them to their charges. You can use the polyatomic ion tables like we gave you on the test here on the back of your periodic table. You can see there the symbol with the charge there so that you get it correct. The goal is to get this correct, and we want to practice like you're going to have the resources in your future. You will have a cell phone most likely at your, close to your proximity. So you'll be able to search these things. That is the table if you're working. So they're going to switch, right? Reaction. What type of single replacement reaction is it? Is it the activity series or the electronegativity scale? Now, is this a metal or a non-metal?
Metal.
Is this a metal or non-metal?
That's non-metal.
Oh, yeah, what's this one? Is it metal?
Metal.
Metal. So this is a metal single replacement type. So when it's a metal, what are you going to look at?
The electromagnet.
You're going to look at the activity series of the metals, right? This is a single replacement reaction involving metals. So we're going to look at the activity series of the metal. Silver being less active than the aluminum, so the reaction is going to take place. We find that the charge on aluminum is 3+. The charge on the nitrate is 1-. We go to the periodic table to find that. You can see on the back we have the common ions, NO3 1-. And then we're going to have a silver metal produced, right? So we have to balance this charge here. We need 3 more of these, or correction, 2 more to give us the 3 positive, 3 negative. So we're going to drop that down here, AgNO3 plus Al yields Al parentheses NO3, 3, because there's 3 of them here, plus Ag. Now, is this balanced? Raise your hand, points. Is balanced? Write this down. Is balanced? No, it's not, because you got 3 here and you have 1 here, so we have to add 2 more. AgNO3, AgNO3. So you can see now that our NO3s are balanced. Our Ags are not, though, so we need to add 2 more. And now we are balanced. So we're going to take our coefficients and put that out front to show the equation is balanced. The first one, we've done the first one on the homework, number 1. The activity series provides you with the list of the activity series of the metals on the opposite side of the homework. This is the easy side. This is the more difficult side. You're going to want to look at this sheet that I just gave you. And you can see that this has to do with metals. These are non-metals, so we're going to want to look at the electronegativity values. You have to look at the activity series or the electronegativity scale, these charts. So you have to evaluate charts. The whole point here is not everything you put together is going to form something new. All right. So if you look at chlorine, Hannah, and we look at iodine, you'll see that iodine, I know a lot of people speed too, like, down the highway, but when you get caught and you got to pay the fine, So up here, iodine has a 2.7, and chlorine's got a 3.0. So chlorine is stronger. It's going to stay bound to the to the metal, so no reaction is going to take place. So there are two that have no reaction. You'll see this in the future. You'll, try to make things work, and then there's no reaction. Now the last one does occur because fluorine is stronger than bromine is. So fluorine's going to say, bromine, you're going to have to leave, and I'm going to take over. So you have to know what the charges are. So potassium's in the first group of the periodic table, so you're going to have one positive there. And the bromine is in the last group, but it's going to be diatomic, so it goes over here. And then fluorine is one negative. And you balance this, so it ends up being KBr plus F2 yields KF plus Br2. Now we have to balance this. Can anybody come up here and balance it?
Sorry.
Yep. And just put the coefficients out front. Now this part is the easy part. The hard part is really figuring out whether the reaction is going to occur, making sure that you're going to form a stable compound that has zero charge. All compounds have zero charge. This is the hard part, because you have to look at the charts. The charts have to be referenced. I don't memorize charts. It's just not something I do. It's not a hobby. Combustion reactions have a predictable pattern they follow as far as the products. CO2, H2O. Activity series has to be looked at for both single and double replacement reactions. If you see lithium on the top, then it's going to be bound with a nonmetal. It's a very good provider. The good providers, they usually get taken pretty quickly. They don't stay around. Gold is non-reactive. It just doesn't want to bond with anything. It's kind of like the Pope or the priests. They don't get married, right? So they fall into that gold. They're very honorable and noble. They just don't react with things. And then you have over here fluorine. She's the most active. She has the greatest desire to produce things. And this would be like Shark Tank. Anybody know some of the women that are on Shark Tank? Have you ever seen that show, Shark Tank? You might know some of the women producers there. There's one who's in real estate, and then there's another one who sells clothing. I don't know their names because I'm not, that big of a fan, but I know they're on there. Okay, I am a big fan of the show, but I just can't remember the names. Lori Greiner, I believe she has produced a lot of aerobics products. If you go into Walmart, you can see some of the things that she's endorsed. Then you have Barbara Concorin. Looks like Concorin. She's big in real estate. So both of these women are going to be very much like fluorine, very high interested in success, right? Very good work ethic, very strong. Fluorine has a very good work ethic. That is, has a strong desire to get another electron. So that's why you see it bonding here with potassium, and then bromine is left out here to the side. It says a metal will replace the cation in the compound. A nonmetal will replace the anion in the compound. If the element is more reactive than the one it attempts to replace, then the reaction will be spontaneous and exothermic. What does exothermic mean? Exothermic? If you have a campfire, is that exothermic? Yes. Why is it exothermic? Because it produces heat. It gives off heat. Endothermic would be like ice. When you grab the ice, it takes heat in. So reactions that are cold, like you can mix things that are cold, are endothermic reactions. They take heat in. All right, so otherwise, it will not be spontaneous and will be endothermic, no reaction. So no reaction is like right here, no reaction takes place. Now you can force it. If it's endothermic, you can force the reaction. It's just going to require a lot of energy to do that. And your success on that would probably be very minimal. You could have a theoretical of almost 0, and actual you might get 1%. Because endothermic means you have to put a lot of energy into it to get it to go. No reaction is going to be the norm. At the chart here, and I find iron. Iron is right here, and is copper above it. Copper's below it. So iron, I'm going to underline iron. I always underline the one that's more reactive. Why do you underline the one that's more reactive? Because there should be something with it. If it's more reactive, this is going to take place because it's a better provider. Iron is a better provider. It means like lithium is a better provider. Alright, so next one you have zinc and hydrogen. You can see here, here's zinc, right? If you don't see the hydrogen above it, then zinc is a better provider. So it's going to go to the zinc. And then we look at magnesium. Now the last one here, you're looking at the halogens. So these are the halogens over here. And you can see that chlorine is above bromine. So chlorine is the better provider. So I always underline it. So if it's underlined, it should be with something else. Because if you're better, you tend to be, you know, together, teamed up, like you're on a team. Usually, if you're, you're playing sports, people pick the better players first. This reference chart is very helpful when you're predicting single replacement and double replacement reactions. I always refer back to it so that I get my ions correct, so that I balance my equation correctly. And then there's the solubility chart right here. Now up here it says all common salts of group 1 elements and ammonium salts are soluble. Ammonium ions are soluble. All common acetates and nitrates are soluble. All binary compounds of group 17 elements with metals are soluble except those of silver, mercury, and lead. All sulfates are soluble except those of barium, strontium, lead, calcium, silver, and mercury, except for those in Rule 1. Carbonates, hydroxides, oxides, sulfides, and phosphates are insoluble. It's really easier for me to just reference this chart here than to memorize the rules. You can memorize the rules, but the chart's just easier for me to reference. So I see iron, I see acetate, there's a blank there, which means no reaction. When you see a P, partially soluble. So the blank is just not going to form a substance. It's more likely aqueous. Now up here, aqueous is important because it says one product must be soluble and one product must be insoluble. That means it's aqueous if it's insoluble. Correction. If it's insoluble in water, it means it's a solid or liquid. So if it's soluble in water, it's aqueous. Like table salt is soluble in water, right? You've seen it dissolve in water. You put table salt in water. Like if you're cooking, that's soluble, aqueous. The one that's insoluble is going to either be the solid, gas, or H2O, which we talked about with the double replacement reactions. There were 3 things to look for: gas, the precipitate, and the water. Alright, so the insoluble product is the precipitate. The insoluble product is the precipitate that forms when the reaction takes place. Usually a precipitate is a solid, but it doesn't have to be. This reaction does take place because the aluminum is the better provider. We looked at the activity series of the metals, which is right here, and it shows that aluminum is higher on the series than silver is. Silver is down there closer to gold, bottom of the box there. So this is going to switch. That is, nitrate's going to go over here. It's a better provider. And when it moves in water, if you put this in water, it's going to move. You have to still balance this. So you have your 3 negative charges, your 3 positive, and then we... Yeah, throw it away if it's dead. So very good. She's balancing the polyatomic ion first. Yes, 1, 2, 3. Nice job. And you can just put the coefficients out front, in front of the... So hydrogen kind of falls in the middle. You've got lead, tin, iron, more reactive than hydrogen, copper, mercury, silver, less reactive than hydrogen. So if we look at lead, we know that hydrogen is going to be beneath it. So when we look at our table that I gave you when you came in, this one right here, if you see lead, hydrogen's right beneath lead. So up here with barium, where does barium fall? Is barium above lead? Anybody see barium on there? Barium falls right beneath. You can see right here, here's barium. Potassium, so it's got lithium, potassium, barium. So it should be right underneath lithium, above rubidium. They don't show rubidium on this one, so but they are showing it beneath potassium. So it's going to be more reactive than hydrogen. So this reaction is going to take place. So most likely this reaction is going to be double replacement because hydrogen and hydroxide form water, and one of the requirements for a double replacement reaction would be the formation of water. So then we're going to get the barium is going to react with the nitrate, NO3, and there's a charge there of 1 negative. So how many of these are you going to need on the barium? You're going to need to add 1 more, so it's going to be Ba, what? O3, 2, right? Because this is 1 negative, that's 2 positive. That's what makes this a little bit tricky. You have to go back to the periodic table and find the charges that are in the groups. You could really spend like 2 or 3 weeks on this, practicing it really to get familiar with it, because it's kind of like a language of itself, balancing the compounds and balancing the equations. You see where it takes place? So barium nitrate, is that soluble? Let's look at the back of the book. Nitrate is soluble in water. So what does that mean about this reaction? Barium nitrate soluble in water. Well, if we have barium nitrate in water, right, can I evaporate the water and only have one substance? Yes, that's the benefit of double replacement reactions that produce water. You can then isolate this and then you can sell it for money. This is valuable now because there's nothing else in there that's going to react with it. You just evaporate the water and you're going to have barium nitrate. This is going to be a salt. You might have a reason to make barium nitrate salt. It might be something that somebody wants to purchase. We have 2 hydrogens there and 2 oxygens.
So is it balanced?
Well, should this reaction take place? Yes or no? Gabriella? Should this reaction take place? What do you think? Yes or no? Yes, it should take place because hydrogen plus hydroxide forms what? Right, it forms water, H2O. And one of the requirements, again, of a double replacement reaction is it can form water, precipitate, or a gas. So then we're just going to make our calcium 2 plus, and then I guess that's, I have to look that one up again. I'm going to name that off the top of my head. Going drawing some blanks. I think it's acetate. Yeah, it is acetate. C2H3O2. The acetate. So you're going to have how many of these? You have a 1 negative and a 2 positive? Right, you're going to have another one, right? to balance that out, so it ends up being Ca parentheses. Everybody see that? Okay. Then we got our water. Anybody want to come up here and balance this? Diane? What? How about Brendan? The trick is to balance these big polyatomic ions first, so then I get all of those fixed. So I have one here, because actually I have two of them here, and I need two of them over here. This was originally just one. See how it's one? So I added another one of this polyatomic acetate so I can balance that. Does everybody see how these two are balanced? This acetate is balanced. All right, now we're going to look at the calciums. The calciums are balanced. It goes back to the water. Is the water balanced? So we have two hydrogens here, and we have two oxygens there. We have one here. That creates a problem. We have a 2-to-1 happening here. So when you have this, the best thing to do is double. Yeah, you got some polyatomic oxygens. Your lithiums are balanced though. So the acetate, you can't forget about the hydrogens. There are two of them there. Over here you have two hydrogens, two oxygens. So that's 4, so you need to have 2 over there. This is a difficult one. Homework tonight, you have lithium and iron nitrate. Lithium has a 1 positive because it's found in the first group. Nitrate is 1 negative. It's found on the polyatomic ion table. They both cross out and you get LiNO3 plus iron. Write that down. Nitrate's the one I'd work with first because you got 2 there and 1 there.
Okay, so this right here.
That's 2 of these. You're going to probably want a 2 there.